Am I audible? Is my screen visible?
Yes, Kavin.
So yeah, it's good. Back-to-back talks. It's been a good week. So yeah, today it's gonna be about one of the most biggest science news. I would say the biggest science news from 2019, the first ever image of a black hole. So why was it really important, and why was it talked about a lot, was something that was discussed in the internet among the general audience and the general public. So this talk would be go through basically what went behind bringing out this image and what is its scientific significance. So yeah, here we go. So this slide is specifically for the observational astronomers who really want to know where things are in the sky. And so M87, it's a Messier object, the 87th in the Messier catalog, and so there it is. And according to the margins made by the IAU, it falls inside the Virgo constellation. So it has a very small angular size, as it is very very far away. It has about 40 micro arc second. So, say for example, if you want to compare that with some other object, Jupiter, for example, has about 50 arc second. So it's million times smaller. So it's very very small. The black hole within M87. So that is the angular size. But don't get fooled by the small size. So these are the actual sizes of the galaxies in comparison. There's home, Milky Way, Andromeda, our neighbor. So M87 is that's the comparison in the actual size. This is a much bigger galaxy. You have IC 1101. So yeah, M87 is a very big galaxy in comparison with Milky Way. It's a elliptical galaxy as well. So one beautiful aspect which we get to see while observing Hubble images here is this wonderful looking jet which comes out of the galaxy from the central part of the galaxy. So why does this jet come? I'll come later on as to why is it only visible on one side, and also that this was the object that was chosen to be taken as a photograph, the first ever black hole. So why did they go for this and not our own Milky Way's central black hole, Sagittarius A star? So the reason was that this, even though being so far away, is an active galactic nuclei, which is actually releasing so much of energy out into space. You can see it. It's bright enough to be seen even from such a huge distance, and it is easier to resolve compared to the black hole in our Milky Way center, which is more smaller and not as active as the black hole of M87. So when you have such a small object, you are not able to resolve it using a single telescope. And as it is at such a huge distance, most of your short wavelengths, like visible wavelengths, get restricted by the interstellar dust, intergalactic dust. So you have to observe it in the longer wavelengths, and so that is where you have to use this method called as radio interferometry. So radio interferometry in a simple way, in a simple model, is over here. So this is the formula, the general formula for the angle of resolution. So the more the diameter of your telescope, the smaller your angle of resolution. So the more resolved your images. So what happens is you can't change your lambda, as that is from coming from the source. So you have to change this d. And what people try to do using radio interferometry is they try to have these multiple arrays of telescopes and try to make one mega telescopic dish out of it virtually. So here you can see one big dish of telescope here, and imagine that you are making it into smaller pieces, but you're keeping it in such an arrangement that, say, if light had focused at the same point when it fell on this dish, it would still focus on the same point when it falls on these separate dishes. And then what you do is you arrange them on level ground, but then as you can move this telescope like this with different heights or different angles, what you do is you calculate the time of separation between the light received on this telescope versus this telescope, and then you correlate all the time gap, so that this image shows that much more clearer. So you have this time gap which is corrected, and you make it in such a way that you get it along this dish, and therefore you have this huge system which acts as a single mega telescope. That is how radio interferometry is done. And for the case of M87's black hole, you needed a telescope which is almost the size of the Earth. So in this case, so these are done in smaller areas. I mean, at a smaller scale, it's done with multiple dishes. But when you need a Earth-sized telescope, that is where your Event Horizon Telescope came in. So this was set up, and it had these set of observatories that were working together. So they themselves are arrays of their own, and you have now a global array of arrays, you can say. So you have so many telescopes working together to create get the data and make the image. So here are a few of the telescopes. Um Alma from Chile and SMA from Hawaii, South Pole Telescope. So here you can see that they're all coming together to form this huge dish, uh, Earth-sized dish that can get the image of the black hole. So how is the data further used? So you receive electromagnetic radiation, the data from various locations, and then that is converted from analog to digital for better transportation and storage. And then you have these atomic clocks. So these atomic clocks are crucial in measuring the time precisely as for this particular step. So this time gap to calculate all and that and for correlating, you need these atomic clocks. And then the data is stored in huge hard drives. So the amount of data is so huge that you needed to transport them around using airplanes. So from that, you transport all your data collected from various telescopes to a single point where it's collected, and then it's combined, and then the data is reduced. So the data is finally reduced to such a form that you can share the image through a low storage device like your phone or uh, laptop instead of carrying it around in airplanes. So before I go to the image which was taken by EHT, these are some popular visual representations of the black hole, uh, of any black hole. So this is a very famous one that led to even scientific papers being released, but was made for movie purposes. It's Gargantua from Interstellar. When it came out, it was said as one of the most exact representation of a black hole in a movie, or even in as a visual representation of a black hole. And but before that, this is considered as the most. This is considered as the first ever artistic image of a black hole. And here, this was by Jean-Pierre Luminet in 1979. So this is the image he made, and here you can see the black hole and the accretion disk. And this actually shows something clear, which can't be seen here, is that you have this brighter region on this side while it's dimmer here. I'll get to that as to why that's there. So here you go. This is the image that was taken, the first ever image of a black hole. And so, what are the various things you can notice from this photograph is what we'll see next. So here you go. This was released by NASA to describe the various parts of this photograph. Um, Other than the jets are visible here, but this is the main part which this diagram will describe. So here you can see that this area is more brighter than here, which you can see here as well. There is this brightened area compared to here. So this is caused by something called as Doppler beaming or relativistic beaming. It's something that comes out as a consequence of special theory of relativity of Einstein. So why does this happen? So here you can see when a source is stationary in the observer's frame, the light being emitted by it is homogeneous in all directions. But once it starts moving, so the light beams start to point more and more towards the direction of propagation of that source of light. And as it goes closer and closer and closer to your speed of light, then most of your light beams get converged towards the angle of in the direction of propagation. So here you can see that in the emitting frame, say your angle is this, and you apply a Lorentz transformation, and you can see in that the observing frame, the angle gets reduced. So when you have this velocity, this angle gets reduced. That is called as relativistic beaming. So when your matter is moving towards you, the light is getting beamed more. So that's why you observe it brighter here. Well, if it's moving away from you, it's the light beams are getting uh, beamed away from you, so it's more dim on that side. So that actually is the reason why you have this bright and dark regions, and also the reason why you see this here, and also the reason why you just see this one jet coming towards you. The other one is on the other side, and so as these particles are moving at almost the speed of light, the light from them is getting beamed towards us, and we can see this brighter than the other jet on the other side. So coming to other aspects of the black hole, so you have this accretion disk, which is basically matter falling inward and getting accelerated due to rotation around the black hole, and it gets illuminated due to the heat generated due to the high velocity and the high energies involved. The matter falling in actually gets ionized and heated up, so that actually emits this radiation. So that is the accretion disk. And what is this top and bottom structure? So that is basically a consequence of general theory of relativity, which says that your light gets bent by gravity. So the light from behind is the accretion disk, which is behind the black hole, is getting bent from above and below towards us. So that is these structures. And then you can see these bands and gaps which are present, which actually aren't very much visible here, but this is a model. So this shows actually something called as a photon ring. So your photons, when they come in, they can go through multiple orbits around the black hole before coming to us, or they can just directly get beamed to us. So depending on how much energy they have, they are usually closer in towards the black hole or further out. So that actually gives these banding and more colored patterns. That actually depends on the orbit each photon takes. So that is your photon ring. And so this black region is not actually the black hole, but is told as a shadow of the black hole. So I'll show you as to why it is. This is from a video by Veritasium. It's on YouTube. I can share it later. So here you can see that, say you're observing from here, and your light from the background is coming through this. So this is your event horizon of the black hole where light cannot escape. So you can see that when light is coming along these paths, which are not actually along this radius, so light which are coming parallelly along these lines too get bent inward to into the black hole. So even a light which is coming from these regions won't reach the observer, and that actually extends this dark portion, which is about 2.6 times the radius of this event horizon. So that is called the photon radius, and so yeah, that is the black hole shadow. So these are the various parts. You can see that here as well. And other than that, so you have this powerful agent and supermassive black hole eating up a lot of matter. So that also tends to generate these jets. So these jets come out when a bit of your material that is falling in towards the black hole gets trapped into its magnetic field and gets thrown out at such high energies. They get such relativistic speeds, and they can even travel out as far as outside the galaxy, which you see here. It's almost going out the entire galaxy. That is your relativistic jets. These are something characteristic to active galactic nuclei. So that was the image. So what was special about this was that it actually confirmed your models are actually similar to what you observed in reality. So before this, people, or whatever people have done, say this or this, were basically based on all the math and all the theory that was put in general relativity. And then you do this general relativistic magnetohydrodynamic simulations to study, to make such models. And once you see this image, you can really see that this model is pretty much similar to this. So you know that your theory is correct and things are working as it should be. And general relativity is correct and Einstein was right. So this actually worked as a verification for the theory of relativity. And so there it was. That is Katie Bowman. She actually did the final part of collecting the data and compressing it, reducing it so that we can see it on our laptops and mobiles. And that was her expression when she saw the black hole image for the first time. It was history that was being made there. And so this was the software that was used, continuous high resolution image reconstruction using patch priors. That was the software used to get the data reduced into the final image that we have. This is the complete team. And so what is coming in the future for Event Horizon Telescope? So they're planning to go and observe Sagittarius A star now, as that is the closest one, trying to make the Event Horizon more powerful to collect more light. And maybe in a more further future, we can launch such arrays into space, uh, which can allow us to observe in more multiple wavelengths as well and collect data in various wavelengths. But that is a more that is a topic for much more in the future. But in the recent past, it's more about making more telescopes and making our current telescopes more powerful. So currently, EHT has been stopped due to the ongoing COVID pandemic, and this is what the founding director Shep Doleman said, which I felt very inspiring as well. So the black hole solution was derived by Carl Schwarzschild in the trenches during World War One. So science continues, and I think it has an important role even amid these challenges. So that's what I feel as well as an ending note. And yeah, thank you.
All right, that was really nice. So, do we have any questions for the speaker?
Thank you. Gravitational lensing. Regarding that, what Misbah Zaman.
Okay.
Okay, I guess no questions then.
Yeah, it was a really nice talk, Kavin.
Yes, thank you. Yeah. Thank
I have one.
Okay. Sure. Shashank.
Yeah. So as you said that he took all the information and made it available in a way that we can see it in our laptops and mobile devices.
Yes.
So could you please elaborate a little more on that process, that how that data was compressed, what was the inputs involved, and how the whole plan worked out, if it is if it is necessary for this talk, if it is in the parameter of this talk.
I really don't feel it is in the this one, but and I am not sure.
Share the details with me afterwards. Let's not waste time.
Yeah, sure. Like lot of coding and all went in. That's all I know so far. So yeah, maybe
Okay,
can
okay.
share links later on.
Okay, thank you.
Yeah.
I mean, you can already imagine the amount of data that they had to transmit. They could not do it over internet or data lines. They literally had to.
Exactly, that was the main reason behind my curiosity. Like, if you're doing even image processing, then that's just few lines of codes and few sequence of softwares. But this is something huge. So I was curious that how they worked it all.
Yeah.
That's the reason why she
Could have-
became a star in the scientific community.
Okay, we have a
Okay.
question in the chat
Okay.
coming.
Why does the shadow not also hide the photon ring? Or I think I might have. Okay. So the shadow. So the photon rings are something that come out, which are shown in the models, but is not seen in the photograph yet, as we haven't not resolved as clearly as yet. But so the it's those particular orbits that are studied, and then you see that at those particular energies and orbits it is able to just go out. And like, if say, so the image which I showed, that was from Veritasium, that actually showed, let me just project it again. So here you have this coming parallelly from backside. There might be also those photons which might be coming at some other direction and going twice, thrice, and going like this, or something, some other angle, some other. So these photons collectively form these thin rings, which are the photon rings. So it's not necessarily that it is coming only this way. So so you basically model all those orbits which the photon can travel along, and then you get these bandings. So that is how you get the gaps and bandings. I hope that clarified. Okay.
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 Okay, so do we have any more questions? You can. Okay, there is another question, Kavin.
Okay. Black hole and golden ratio. There could be there. I am not aware of anything though. There could be there. Someone who's maybe more into black holes can tell if they know. I am not aware.
I'm pretty sure a mathematician would say yes. Okay.
I guess we can go to the next talk then. In case.
Okay, yeah, sure.
Yeah.
Before that, a note for you guys. So tomorrow we have a big announcement on our Insta handle. We will be actually introducing an event called Experiment Mania. It will be a 2-week long event, and the details will be mentioned in the post. But know that your input will be very necessary for this event, and there's also a surprise waiting within that event. And yeah, and keep an eye on our Instagram handle, and yeah, do participate. Thank you.
Okay. Okay, I guess now we can move on to the second talk of the day. Are you able to see my screen?
Yes, yes.
Yes.
Okay, good. Okay, so my talk is going to be mainly about the detection of gravitational waves and a few interesting facts about it, which I found aren't really popular. So, yeah, let's proceed. So, if you had attended the IBAC session a week or two ago, the talk by Abhishek Swain, you'd know that there are three messengers, three major ways through which the universe tries to contact us and give us info about itself, convey us info about itself to us. The first one is electromagnetic radiation. We look at the sources at various spectra of electromagnetic radiation, each one of which tells us a different bit of a story about the source. And the second one is particle radiation. We look at the particles emitted by various sources. When we talk about, let's say, cosmic rays or solar winds, we are talking about the particles emitted from sources outside the solar system and the sun, respectively. So we put together all these pieces of information and try to understand what is happening out there in the universe. And of course, the more information, the more data we have, the better our understanding will become. And so in the past decade, we have discovered what is the third way through which the universe tells us about itself, which is through the gravitational waves. So the theoretical prediction of gravitational waves was made as early as in the 19th century, which the history of the history I'm going to briefly talk about later a little bit. But the first ever detection was uh, made on the 14th of September 2015. The work was published in the Physical Review Letters on 11th of February 2016 by the LIGO Virgo collaboration, almost a century after theoretical predictions. And then there was a Nobel Prize in Physics, 2017 Nobel Prize, which was awarded to uh, 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 Kip Thorne, Rainer Weiss, and Barry Barish. Uh, so yeah, and the signal was named GW150914 for the date the signal was detected, 2015 September 14th. So on the right of your screen, you should be able to see a figure which is stolen right out of the physical review papers that was published by LIGO and Virgo. And so the first chart that you see there is the observations that they had made. This was the data that they collected after a little bit of filtering that they do, or not a little bit. So yeah, this is and the second chart that you see is the numerical prediction from the general theory of relativity that is made by modeling the system uh, in on our computers or through different methods. The system we are talking about is a black hole merger taking place 1.3 billion light years away. The black holes are 29 and 36 solar masses. The data I am taking from Wikipedia, and the final black hole, the resultant black hole was 62 solar masses, and so there is a discrepancy of about what 29 plus 36 is 65, so about 3 solar masses, which was radiated out in the form of gravitational waves. And 3 solar masses is a lot of energy. And so it is said that again from Wikipedia itself, that the only in the last fraction of the second of the merger, the system is said to have outputted more than 50 times the power output of all the stars in the observable universe combined. So yeah, that is a pretty crazy scale of energy, as well as usually it is the case in astronomy, I guess. So the signal, as you can see in the fourth diagram, rose from being about 35 hertz to 250 hertz in a matter of a fifth of a second. And the signal grew as the signal grew stronger as well, which should be a fingerprint of a merger if you think about it intuitively. So let's talk about the detectors a little bit. So the detectors at LIGO and Virgo are basically a modified version of Michelson interferometer, which has a light source and a beam splitter which splits the light into two perpendicular arms, which have a reflective mirror at the ends, and which reflects the light beam back onto a photodetector, which has a certain interference pattern on it, which will change if the arm lengths are changed. So when a gravitational wave comes into the system and causes a strain in the arms of the detector, which changes the lengths of the arms, and so as a result, the phase difference between the two recombining beams will change, and the pattern of the interference that you see as a result will also change, and that is how you detect the gravitational waves. Uh, so these instruments are very sensitive instruments. The and the sensitivity depends on the arm length of the detector. At LIGO, these people have 4 kilometer long arms, and then they increase the path as well by resonating the light beam again and again inside the arms as well, increasing the effective path that the light has to travel. Uh, so yeah, these detectors are pretty sensitive, and which obviously brings about the problem of noise, which is dealt with using various methods that they have. So uh, let's move on to a few lesser known facts about gravitational waves. So the first one is probably pretty least surprising, I guess, of all that I'm going to mention, is that the fact that gravitational waves have their own spectrum, just like electromagnetic waves. So uh, there are various wavelengths and various frequencies at which the gravitational waves are emitted, and which also brings about the disparity in sources as well. So we have different kinds of sources, like rotating neutron star and like, let's say, merging black holes, as was the case of our GW 150914. So these kind of sources are continuous sources. They produce in not a very huge band of frequencies, but there are other stochastic sources as well, like the quantum fluctuations in the early universe, which produce in all kinds of frequencies. And the frequency range of the LIGO detector lies in about 60 hertz to 7 kilohertz. Don't take the numbers very seriously. Again, these are from Wikipedia, but uh, look at the range of the frequencies that we can already observe. I mean, it's pretty early in the field of gravitation. The field of gravitational wave astronomy is very new. In a sense, we can say that we are in the Renaissance era of gravitational wave astronomy. It's just like Kepler, who has newly invented the telescope. Sorry, was it Kepler? Okay, I'm bad at history. So anyway, this is a very early stage of gravitational wave astronomy. So it's quite impressive that we are already able to map such a huge range of frequencies. So, as I mentioned earlier, that there has been another Nobel Prize in physics related to gravitational waves. 2017 wasn't the only Nobel Prize. So in 1993, Hulse and Taylor detected radio waves coming from the pulsar, which is now dubbed as PSRB 1913 plus 16. Uh, so observations led to the conclusion that this object was actually a binary system rotating around each other, and eventually it would both of the constituents would collapse onto each other, and the time period of their orbit was decreasing as time passed by. So in a system like this, general theory of relativity predicts that the system should lose energy through gravitational waves, and the time period shift should be faster than the system where when there are no gravitational waves. So what Hulse and Taylor did is that they detected the cumulative period shift over a couple of decades, and they found out that the predictions matched pretty well with the blue line here, which is the prediction from theory. So it was an indirect detection of gravitational waves, as it is a confirmation as the system is losing energy to something. Whether it is gravitational waves or not, it was yet to be discussed, but that was the best theory that we had at that time, which matched our observations. So it opened up a new debate in the field of gravity, uh, which is for which they were given the Nobel Prize in Physics. And the third, as I promised, talking about the history of gravitational waves a little bit. So the idea of gravitational waves was, well, at least according to the records, was conceived by an self-taught electrical engineer, Oliver Heaviside. You might not have heard of him. He's not a very famous name, but his contributions to physics and science in general are pretty huge. He was the one who introduced the vector notation in physics. He was the one who introduced the complex number notation in electrical engineering, and he was the one who predicted the presence of ionosphere. But anyway, he also gave the idea of gravitational waves. He was among the first ones to do it. So what his argument was that both the electromagnetism theory and the gravitational theory, both of them have inverse square law, but we have electromagnetic waves. So why don't we have gravitational waves? I mean, obviously his argument was much more sophisticated than that, which you can look it up if you want. I'm not going to discuss it here. But the fact that he was the one to discover. He was the one to conceive the idea, which stirred upon the debate. And yeah, here we are now. So later on in 1905, Henry Poincare was the one who mathematically predicted the waves using Lorentz transformations. He found out that the speed at which these waves should travel is actually the speed of light. And then, yeah, as we know later on, that Albert Einstein was the one who gave a complete theoretical formulation of gravitational waves using his theory of relativity. And yeah, his predictions were confirmed a century later. And so, talking about big names, Richard Feynman also had his input in the debate of whether gravitational waves carried energy or not. He proposed a simple argument. So let's have the system where there is a rod, a solid metal rod, over which we have two freely moving beads, which have a friction with the rod. So when this kind of a system is exposed to gravitational waves, the length of the rod will be kept fixed by the atomic forces, but the proper distance between the beads will keep on oscillating as the crests and the troughs of gravitational wave pass through the rod. So the beads will start moving on the rod, and the friction due to the movement will produce heat. And well, the only uh, logical explanation to heat being produced is that gravitational wave energy is being converted to heat. So that would mean that gravitational waves must carry energy. So it is a pretty simple argument. Well, you might be aware of this from one of the quizzes that were conducted through our Instagram handle. But yeah, anyway, another fact about this argument is that he's notoriously known to have taken up the whole duration of 1957 conference. He gave the argument under Mr. Smith. So the whole duration of the conference was taken up on the discussions of this argument, which I find is quite similar to what happens to most of the physics club talks when we are there on the campus, not so much on online platforms, sadly. Uh, yeah, we have an idea and we just keep on discussing on that, and the whole duration, the time just flies by. So anyway, yeah, this was the Feynman's input on understanding of gravitational waves. And so the last fact that I have is a failure, which is quite sad, but at the same time is quite inspiring. So around 1968, Weber had built these these metal bars, which were supposed to resonate as a gravitational wave came and hit them. So this was this was the way that he proposed that gravitational waves could be detected back in the day. But the main problem with this was that uh, okay, so yeah, it had these piezoelectric sensors on the perimeter of these rods, which would measure the pressure changes, uh, which would then detect the gravitational waves. But yeah, a problem with system like this is the changes that we usually talk about are very small. So uh, and there is noise due to thermal motion, uh, which unfortunately produces a very bad signal to noise ratio in such kind of a setup, which is why his readings were rejected by the scientific community back when he published them. So yeah, the signal to noise ratio was a problem uh, with this setup. There were various attempts to save this setup. They even tried to liquid helium cool the system to 4 Kelvin, but it's still the signal to noise ratio was still pretty bad. And yeah, overall this was not a great idea. And I mean, it also drained a lot of their money, so this was not very financially a good idea to detect gravitational waves like this as well. So there were various problems with it. I found a very nice a newsletter from one of the people who actually was involved in the project, which I'll share later, maybe as a follow up of this meet. But yeah, this failed attempt served as a inspiration for people to look into other methods and to detect gravitational waves. So I still consider this as a win overall in in the in the genesis of this new field of astronomy which has come up, the gravitational wave astronomy, which I feel has a very bright future. So yeah, I guess that's it about my talk. It's pretty short talk. Uh, so yeah, I'm open to questions now. Yeah, yeah. So you can ask questions on both of the talks, Anna, if you want, if you have any. Feel free.
So Chirag,
Yeah,
hello.
yeah. Go ahead,
Yeah,
Saksham.
so there are two types of So we now know that there are two types of gravitational waves, right? Like according to the propagation, the plus and the cross ones, right?
Yeah.
So in this setup, were only the plus ones discovered?
I'm actually unsure of if this setup could
Hello.
measure different polarizations of gravitational waves, the plus and the cross polarization. But uh,
Yeah.
I believe from what I have read about
Okay.
them, it could. I'm not sure about it though. Uh, I guess I guess I can share if I find a resource on that. I guess I can
All
share
right.
that as a.
Also, so if like I am assuming because what
Sorry, your voice is cutting off.
All right. Also, like because when I read it about it, it said that it. Hello.
Yeah. Yeah, go ahead, Saksham. Okay. Okay, I guess if speaking out is a problem, then you can type your question in the chat section, maybe.
Yeah. So, by what I read about it, like we discovered the positive, the plus polarization of the gravitational waves. So I always had this confusion that the we detected it because
I'm sorry, your voice is cutting off. Not able to make out what you. Okay, so Padbhaya has mentioned a fact about the Michelson interferometer that it can detect the plus polarization only due to the geometry of it. I'm still not sure about Weber bars though, if they can measure both of the polarizations or not. I'll look into it more and come back about it. Okay, so there's a question by Mispa Saman. Is it true that the gravitational waves can squeeze us and crunch us as well if they have proper magnitude? I am I'm really unsure of that. Uh, maybe Dada can answer this. Saksham, the plus and the cross polarizations are predicted by the theory itself. Uh, yeah, when you do the mathematical calculations for the gravitational waves, and you look at the equations and all, you'll be clearly able to see that there are two different kinds of polarizations that it follows. So I will also maybe share the ISSAA lecture, the introductory summer school in astronomy and astrophysics lecture, uh, which was given by Sanjeet Kumar, I guess, if I'm remembering the name correctly. That was a really nice lecture, and it explained all these in not too much detail, but as much detail as uh, we could understand, I guess. But yeah, yeah. So he mentioned about where these plus and cross polarizations come from. So I'll share those lectures as well. Yeah, about Dada, do you have something about Misbah's question? I'm unsure if uh, gravitational waves can actually produce pressure on you, stress in your system. I mean, if you look at it like this, gravitational waves do produce strains, right? And stress and strain are related to each other. So uh, I guess they should be given hard enough gravitational waves. They should be able to crush you. Although I would not wish that such a scenario ever occurs.
If you're close enough to a source that is generating gravitational waves of such magnitude, I guess the other factors would take over before gravitational waves, like
Yeah,
a exploding
yeah, yes.
merger of a neutron star black hole.
Yeah. Spaghettification would be a bigger problem.
Yeah, like other
There.
factors can, but in general, if you're seeing just waves, I'm not sure.
Yeah. Okay. Dada, if you have something regarding this, I guess it will be helpful. Why is it believed that? Okay, Rita asks, why is it believed that a mass distribution will emit gravitational waves only when there is a spherically asymmetric motion against the mass? Can symmetric motion or systems not produce them? Okay, so about this, uh, there's going to be a lot of terms which I can't explain in a easy way. So there is something called quadruple moment. Uh, okay, how do I put it? Hmm. Let me think about it a little bit. Hmm. Okay, so what I'll just mention the fact here that there's something called the quadruple moment of an isolated system's stress energy tensor. So if you look at the equations which govern gravitational waves, the second derivative of that quadruple moment appears there. So the requirement is that quadruple moment, the second derivative of the quadruple moment should be non-zero for it to be able to emit gravitational waves. And so that only occurs when you have asymmetry in the system. Like let's say you have a dumbbell not rotating about its axis. Like when you have a dumbbell rotating about its axis, that is still spherically symmetric system, or at least rotationally symmetric system. I'm sorry. So in that scenario, you will not the system will not radiate gravitational waves. Okay. Yeah. Yeah. I mean, I'll give a few resources if I can find some.
What
Uh,
is symmetric motion in the system?
Sorry.
what does symmetric motion or asymmetric motion here mean? Like, is it asymmetry in the mass or in the type of periodic motion?
Yeah, asymmetry in the mass distribution and the accelerations of the masses.
So if we have two equal neutron stars colliding, they won't produce G wave.
They will now. They will.
Okay.
So a system like a perfectly spherical supernova explosion that has a spherical symmetry. So that system like that would not produce gravitational waves. Yeah, asymmetry in the mass distribution of the whole system
Okay.
is what is in the simplest terms produces gravitational waves.
Okay.
But yeah, the ultimate fact is the second derivative of the quadrupole moment of the stress energy tensor. But yeah,
Can you physically explain why symmetry mass will not produce gravitational wave?
I guess I'll require Dada's insight for that.
Okay. So,
Dada? Yeah, because he's the one who has taken up all the GTR uh, courses. Yeah, okay. Dada has some problem with the mic. And I guess this is a very elaborate explanation, so don't want him to type for days. Yeah, I
Yeah, we
guess
can
we
have it
can
later.
discuss this. Yeah, we can discuss this in the discussion forums, I guess. Or yeah, I will also send some sources on this which I can find maybe. There's another question. Is there any by Ms. Basman? Is there any information about the quantum gravity research going on? I'm not sure if it is relevant to today's topics. Um, yeah, I'm unaware of quantum gravity research. I am not really, yeah, I don't really follow research level topics as of right now. Yeah, it's okay. Thank you, Apurv. That means a lot. Thank you, Misbah. Thanks, Paro.
One question, Chirag.
Yeah, sure.
Since you have taken electrodynamics course, I want to ask, is there any constraint to electrodynamics, to electromagnetic waves, like we have the constraint of asymmetric and symmetric motion? So is there means drawing parallel between electromagnetic and gravitational waves? Is there any such constraint in electromagnetic waves?
So in the electromagnetic, so to generate electromagnetic waves, you need accelerated charges, right?
Yeah.
That's what you need. Uh, so I guess you could argue that here as well, it's a case that you need accelerated masses. But yeah, I guess I'll have to think about it. This is a good point. This is related to the argument that Oliver Heaviside made actually. Uh, Let me see if I can find something related to that.
Okay. Okay.
Mm, Yeah, thank you for bringing this up. I'll have to read more into this to actually see if the analogy works like that. Uh, oh yeah, this is another point. Yeah, electric charges are bipolar, whereas gravitational are not. So yeah, this might be relevant to the fact to the discussion here. Because yeah, okay, maybe not. Okay. Yeah, there's a line mentioned in one of the Wikipedia pages that I've I came across is that the yeah, as I mentioned, that the second time derivative of quadruple moment is must be non-zero to emit gravitational radiation. So the Wikipedia says that this is analogous to changing dipole moment of charge or current that is necessary for emission of electromagnetic radiation. Okay. Regarding sharing the WhatsApp group link, actually the core team had decided to make it a group which is close to uh, either people only. But yeah, I can surely consider this point, and maybe I can DM you on Instagram if that's okay, Misbah, with the join link if we decide. Yeah, we can have a discussion regarding that on Instagram DM. Yeah, yeah. I'm sorry. Yeah, I I agree that I'm guilty of citing Wikipedia a lot of times. Okay. Okay. Uh, Yeah, feel free to unmute yourself and talk as well if you have any points to discuss. So a follow up of this meet should be coming to you soon. I'll try to send it as early as possible. So yeah, you should have all the resources and all mentioned in the talk uh, pretty soon. So yeah, keep an eye on our Instagram handle. We have a special event coming up as mentioned earlier. And yeah, please do try to attempt our question of the week. There are some really interesting questions which we post on our Insta and FB pages.
I'll ask everyone present here to actually try this week's question. And you have 2 days until Sunday, 5 p.m. You can give it a try actually. It's a very interesting question. So please give it a try and send us answers via DM or email.
Okay. So I guess if there are no more questions, that then we can end today's meet. This was the first time we conducted two talks online, and yeah, it is a wonder that we were able to finish it in 1 hour. So yeah, thank you for being such a nice audience, and I hope you take away at least something from today's talk. Yeah, thank you.